So, this is generated by a single element with relation equal to 1. So, when do I have a group homomorphism from this to any group? As long as I can find an element whose cube is 1, I have a representation, I have a morphism from this group to that group, namely sending S to that particular element whose cube root is identity, right? Whose cubed is identity. Thank you. Whose cubed is identity, I should say. That element is a cube root, so to speak, of 1. Okay, maybe the word cube root is not very nice to use if the group is not. Anyway, whose an element whose cubed is 1. Okay. So now, and we have seen that you must have this is the it must be a map to GL1C, no choice. In fact, we have even seen that it must map to the circle group. Z by 3Z, thank you. Z by 3Z. Right? So, same thing. That's also correct. Nothing wrong with if I write, but for this context, it is Z by 3Z. Correct, absolutely. So, for Z by NZ also it is okay. This is the same logic. Okay, so it has to go to S1, not only to C star. Okay. Anyway, that is not hard to see because it has to be a complex number whose cubed is 1. So it can go to omega or to omega square. Moreover, I can specify that arbitrarily because the only relation is this. So it's an if and only if condition. If I can find an element whose cubed is 1, lo and behold, I have a representation. So I write omega square here, and these, you might want, you could give some names to these. Just a matter of, I don't know, I don't remember now. Okay, I don't remember. Okay. In any case, you can check the book. Yeah, row 1, row 2, row. Maybe. I don't know. Okay. The column, the rows of this character table correspond each to one irreducible representation, and that row gives the character of that representation. Characters by? You could, of course, you could name them chi 1, chi 2, chi 3. Yes, yes. So 1, 2, 3 up to the number of conjugacy classes, right? You could do that, yeah. Of course, that's notation is in our hands. So, and maybe there is standard notation in some cases. Maybe you have to make up the notation as you go. Maybe you have to change it to your particular context, whatever it is. But is it clear? Right? Okay. Now, let's do this one. Right? So, what is the size of the character table there? 4. Why? Because it's an abelian group. Simple as that. Okay? Okay. Now, maybe you can help me. So, it's a 4. So, how do you want to write elements of this? Okay, you can think of it as a square equals 1, t square equals 1, st equals ts. Right? You have to put that condition, otherwise it is not quite right. Okay, that's one way of thinking about it. Another way of thinking about it is just plus minus 1, comma plus minus 1. It's this cross this, the Cartesian product of two groups. Yeah, or let me write 1, 1. 1 minus 1 1 1 1, minus 1, 1, minus 1, minus 1, 1. I am just thinking of this therefore as this is a Klein 4 group as plus minus 1 cross plus minus 1. It's a Cartesian product of two groups. Right? So, okay, tell me what the columns, rows should be. Of course, the first one is trivial, everything goes to 1, and what must the first column be? 1, 1, 1. It's an abelian group, so everything, all the dimensions of the irreducible representations, recall that these numbers that you see are the dimensions of the irreducible representations. They must all be 1. Okay. Now, how do you think of this? If you think of what, as Avijit was saying, this has one generator, this has one generator, right? And there are 2 plus 1, 3 relations. S square is equal to 1, T square equal to 1, ST equal to TS. Okay? But the ST equals TS is sort of immediate because I'm going to take my, I'm going into C star, which is an abelian group. Therefore, ST equals TS will hold by itself. There is no condition because the image is abelian. That's no condition at all. Okay? So, I have ST equals, S square equals 1, T square equals 1 are the two relations I must make sure that I satisfy. And conversely, if I make sure that those relations are satisfied, I do get a representation. It's an if and only if condition. Right. So, S square equals 1 means how many choices does S have?
So, what is ST equal to TS?
Is obviously satisfied because the image is abelian.
So, but ST, S and T are elements of the group, right?
Yeah, you can think of this, I am saying, you can think of this as with two generators, ST, and with 3 relations. S square is equal to 1, T square equal to 1, and ST equals TS. Right? You can think of that. So, once I want a map from, I mean, a group homomorphism from this group to some group, which means I have one element, which is the image of S, one element for the image of T. I have to make sure that they commute, and then the squares are equal to the identity. Okay? What I am saying is, since I am taking images in C star, and this is an abelian group, this I need not worry about. That's automatically satisfied. So, I only need to make sure that S square is 1 and T square is 1. What are the choices for S square therefore? Yeah, for the choices of S therefore. Yeah, which is 1 or minus 1. T has 2 choices, plus or minus 1. And anytime I have, so those are the 4 choices that I have. That will determine all the representation. So, this is S, this is T, right? And this is ST if you wish. So, this could be 1, 1. Minus 1, 1, 1 minus 1 or minus 1 minus 1. And depending upon that, this is just the product of these two numbers. So, this is minus 1, minus 1, 1. And once again, you can, whatever names you want to give them, you could call them chi 1, chi 2, chi 3, chi 4. Is this clear? Okay. Let's do, how about Z mod, oh I forgot, okay, Z mod 4Z is here. Z mod 4Z. How about Z mod 4Z? Same. So, let's do Z mod. Is Z mod 4Z clear? If it is clear, I won't do it.
In fact, Z is
Z mod NZ is clear, right? Because you take the generator, there is only one condition Sn is equal to 1. So, you choose that. So, if I write my first column is this and the second column is this, where this I think of as the generator. and here it will be 1, 1, 1, 1, 1, 1, and here it will be 1 e to the 2 pi I over n, e to the 4 pi I over n, and so on.
Omega. Right, omega.
And if you write omega or
Omega square omega.
yes, omega or let's use some other letter. Omega, what's the standard
Yeah, that is
zeta, zeta square, zeta to the n minus 1 here, and zeta to the n is 1. So, the right, and s square will be zeta square. S square here will be zeta to the 4, whatever that is. S here will be zeta to the 6th, and so on. The next element will be s cubed, which will be zeta cubed here, zeta to the 6 here, and so on. Right? All right. So it's determined by this. So this is okay. This is okay. This is okay. Correct. And notice that this is a good way of generating orthonormal. Of course, there is a these are orthonormal bases for R4 with the given inner product.
because cardinality is one equivalence classes cardinality is
Yes.
and G cardinality is given
Yes.
by that.
Yes. So that's a nice way of generating. See, this is related to several things. For example, you can think of this as a Van der Waals. Okay, so you can. I mean, obviously, this has got something to do with the.
Is characteristic something or
Yes, like I said, there are so many things you can do with the character. The character table has beautiful structure, right? If you look at group theory books, I mean they go on and on and on and on, and there's no end to it. Okay, you can enjoy this for the rest of your life.
handling people is big task.
Huh?
For
No, but
SN
no, it
for
is.
SN it is big task.
Well, yes and no. There is many things that are known, many things that are not known. I mean, like I said, it can lead you very soon into research areas. For example, a recent Fields medalist from 2006, Okunko. One of his works, cited works, I think, is work on the representations of the permutation group, representations of SM. That's not the only thing he did, of course, but he and along with his teacher, I think Vershik, had a different approach to representations of the permutation group. It's called the Okumkov-Vershik view or point of view. That paper is at your level, and some of those papers are things that you could start reading right away. Okay, they are not so difficult. Okay.
Sir, one thing. Here was relation was quite trivial because you said ST equal to TS equals to. But if suppose where the relations, the images of the relation is non-trivial, you need
Yes,
some condition.
you need some. Yes.
That time some
Yeah. Okay. Yes. No, I am not claiming that finding the character table is a piece of cake. I did not claim that. Okay. So it's not a piece of cake, but it's very pleasant, and of course for small groups of small order, you should do this by hand. Okay, so maybe we will talk about the dihedral group today. I want to talk about the dihedral group.
that representation.
Huh?
Representation of the dihedral.
Yes, character tables of dihedral groups of any order. Of any order. Let's try that. Okay, as an example. Okay, S3, right. So we have done with everything except S3 on this list. Right. So let's do S3. So let me erase everything. Character table of S3. Maybe S4 as well. right? At least let's get started on it, okay? Okay. So, so let's start.
Sir, trivial representation the vector space has dimension 1.
Trivial representation always has dimension 1, otherwise it won't be irreducible. Here, of course, it cannot be 1, 1, 1 because not abelian, right? So there is going to be at least some number which is bigger than 1. Okay, so if you think, so this is for S3. Okay, now there is, I will represent so that's a conjugacy class. It has 3 elements, and this is a conjugacy class. This has 2 elements. Right? Of course, here it is 1, 1, 1. Right? Recall always this group has a sign representation. Namely, you send even permutations to 1, odd permutations to -1. Another way of thinking about it is the following. See, whenever you have a quotient group, see, it's important to have, how do you generate representations? Interesting representations. It's always a very pleasant thing and a very important thing. One observation, trivial observation, but important, is if you have a quotient group, all its representations are representations for the group. If you have a quotient group, if I am seeking the representations of A, G, and if I have a quotient H, any irreducible representation of H can be thought of as an irreducible representation for G, just by pulling it back. So that definitely that's one way of generating. Okay? So the sign representation comes about because you have this map. Oh, sorry. Because this is a quotient by the normal group, normal subgroup AN. So, and this has 2 representations. Right? So those are the 2. So this is that one. So this is an odd permutation. This is an even permutation. Yes, if it's a simple group, for example, that doesn't get you anywhere. Correct, absolutely. Point well taken, but observe that very often, for example, dihedral group, there are cases, right, when there is a quotient, right? D10, I mean D20, D10 is a quotient of D20, D5 is a quotient of D10, right? So D8 is a quotient, D4 is a quotient of D8, no, Dx is a quotient of Dkx, correct? So that already gives you some information about Dkx, okay? So none of this is foolproof, none of this is, you have to use something or the other in every situation, okay? But there is no recipe, so to speak, but you do use whatever is available. Okay, so now there is only one more because the size is 3 and that has to be 2.
So how will it sign so if odd goes to minus 1, even goes to
Or you just think of the other way to think about it, that's one way, but you should also think of it as, look here, this is the group, I think of this representation, and then pull back that. So there are 2 representations of this, namely the trivial and the sign. So these are the pullbacks of those representations to Sn.
So if we have irreducible representation on a quotient space, the
The-
corresponding will be
Absolutely, it will be reducible. It has to be. That's an easy thing to proceed because whatever is an invariant, mind you, if this is a onto map only, right? If something is invariant for H, if and only if it's going to be invariant for G, because G is acting via H. That's an easy exercise.
GH, yeah. G goes to GH and then
Yeah, exactly. Exactly. So irreducible representations, when you pull them back, if the any irreducible representation for H is a in fact any representation for H, if you pull it back to G, it's irreducible for G if and only if it's irreducible for H. Okay, so and this has to be 2, right? Why? Because this square plus this square, there is only one more, and the number that must be here is the square of this plus the square of this plus the square of this must be equal 6, right? So this must be 2. It cannot be 3 because 3 square is already 9, it's too big.
dimension of A square, dimension of B square, dimension of AB square is equal to pi by 2.
Yeah. So it's 1 plus 1 plus something square. X square plus 1 plus 1 is equal to 6. If you solve this equation for x, you will get x square equal to
CG, that one was for CG.
no. That no. We deduce that by looking at CG. See what we deduce. See the theorem is that the we have this formula. We deduce that by looking at CG. Okay, we deduce that by looking at CG, right? But this is because the way we deduced it, if you remember, we decomposed chi g, right? See, let's recall once again. How do you, if V is any representation and you want to write it as a sum of irreducibles, and if you have a list of irreducibles, then what do you have? You have V1 to the chi V chi 1, right? Where V1 to V1 is the list of irreps, right? And chi 1, chi n are their corresponding characters. This comes about because you have the orthogonality of right? Yeah. And then we saw that if I take if I put V is equal to left regular representation, I am repeating what we did. Right? And then we saw that chi left reg, meaning with chi j, if you take this, if you compute this, this was equal to dimension of Vj. Or you can write, you can write one more step, is chi j of 1 is equal to dimension of Vj. Okay, so I am telling you that see the you can see, you should not think of this. I want you to, I invite you to think of the proofs as we are writing this, right? How did we write this? Well, this is because you can write an A1 here, AN here, and compute that AN, right? So how do we get this? See, you will write V1 is equal to V1 A1 plus Vn direction AN by complete reducibility, right? And then so chi V therefore is A1 chi V1 plus AN chi N, because the chi of V1 direction V1 is 2 chi, chi V1, chi of V direction W is chi V direct plus chi W. That gives you this. But now I apply chi V, chi J. Now these are orthogonal. So this is AJ, chi J, chi J. So the AJ is equal to this. Now I substitute this here and get that. Okay, so this follows from the orthogonality of no, maybe it is Frobenius orthogonality of characters. Doesn't matter. Okay, orthogonality of characters, whatever we have proved. Okay, okay. It may be. I don't know whether it's sure or.
Sir, my question.
One second. Now I take the left regular representation and apply this. Then I claim this. Now this is an easy calculation, I claim. Why? Because this is easy to see. The point is, this is easy to compute. So by definition, what is it? You compute the matrix and take the trace. If I take any G other than 1, look at a basis for the left regular representation. It consists of group elements. If I left multiply by any element other than 1, everything permutes, nothing is fixed. So therefore there is nothing, there is zeros on the diagonal. So this is, we know that this is equal to, so this as a function chi left reg G is equal to 0 if G is equal to, G is not equal to identity, 1 if G equals identity. Now use the definition of this. What is it? This is by definition therefore 1 over G, sigma G in G, chi left reg G, bar chi J G. But this is 0 except when G equals identity. So the only time I get this is when G is identity. The rest of the sum is always 0 except there is only one term. Okay? So it's 1 over G chi of, here I did it. Correct, thank you. So it is 1 over G, so then it is G into chi J 1. So we have done this. But chi J 1 is the dimension of Vj, because chi J of, this is just an observation, chi V of 1 is always the dimension of V for any representation. All right? So this is a generality, and for this is the proof. Okay, so when writing this, I'm giving you also the proofs. The proof should run in your head. These are not facts to be you know, the proofs should run in your heads when you use them. So now apply this to the left. So combining these two, you get this, right? You put V equal to left regular representation in this, you get this, because, and then you take dimension on both sides. Okay? Yes. Okay. Now your question. Yes. Sorry.
But this maybe V equal to A1 can direct sum of A1 by putting that A1 is a very A1 times.
Yes.
A2 times A2 times.
Yes.
So always it is true that you are getting a positive number and positive integer.
Always by
so
so
what you think is V, that if a row rho acting on the representation, the rho. You are decomposing
No, no.
into irreducible subspaces, right? So how you
No,
get
no,
V1 to cut?
think like this. How did we do? Start with V. If it's irreducible, then it's done. If it's not irreducible,
V1 directs on V2.
if this is irreducible, done. If not, break it up. If not, so you will always get an integer, right?
So what I'm saying is this V1 directs on V2, that V2 may be equal to V1 you are saying, it may be possible.
It might be possible.
Then dimension of vector space, how would be that sum of this, because what is the definition of direct sum set? V1 intersection V2 has to be 0 element, right?
No, see, you're confusing between V1, what is a two-dimensional vector space? It's a sum of two one-dimensional vector spaces.
Sum of the one.
But those one-dimensional vector spaces are isomorphic.
Yes, they are isomorphic.
So, but it's the direct sum of one line plus the another line. If I take two lines like this,
Intersection may not be 0.
intersection is 0. They are isomorphic, but physically they are not.
Well, intersection is non-zero.
Yeah. So V1 could be isomorphic to V2. But V1, now we are not talking inside V. Inside V, V1 is physically distinct. V1 intersect V2 is 0. Does not mean V1 is not isomorphic to V2. V1 could very well be isomorphic to V2. V1 is a subspace of V. V2 is a subspace of V. So you intersect these two subspaces, you get 0. Like two lines. They are isomorphic as vector spaces or representations for the trivial group if you wish.
But sir, how are you getting multiple positive number times?
Because look at this process. You are taking V, breaking it up into pieces. Again you break it up into pieces. It's always an,
V1, V2, Vn you got.
I got V1, V2, there are 10 things. This is counting, right? You always get an integer. It's a sum of so many, it is V1 plus V2 plus V3 plus V4 plus V5, etc., etc. This, I will not get 4.5 representations.
So that is integer I'm saying, but V1, you are saying isomorphic copy of V1 are A1 or what?
So what I do after that, when you write that, what I mean is, you decompose in whichever way you have.
Yeah,
V1, V2, okay, V3, V4, etc.
Yeah.
Now, okay. Now okay, let us use a different notation. Let's take U, okay. Let us take U, let U be a representation and write U1 plus U2 plus U3 and so on. Let's say UK or UN. Right? You can do this. This is just by, if U is not irreducible, break it up, this, break it up, etc., etc. Right? Okay, done. Now, when we write that, what we mean is, out of these you check, see V1, V2, Vn are given fixed irreducible, this is the complete list of irreducible representations for your group. Now, this U1 must be one of these. This U2 must be one of these. This U3 must be one of these. This is the complete list.
One of them has to be equal to.
Yes, U1 must be isomorphic to one of these. So when we write that, what we mean is, you collect together all those that are, collect all those that are isomorphic to V1 and write it as V1. So when we write informally this, what we mean is the sum of all these which are isomorphic to V1. The sum of all these which are isomorphic to V2 is what this is. And is this clear? Yeah? Yeah? Is this okay? Okay, good. Good. So once again, don't see, there are two things. Isomorphism, but physically, see, when you are talking about isomorphism, when you are talking about physically being the same or distinct, subsets of some bigger set, these are important distinctions. Okay, now coming to this, right? So we want to compute this, right? One way you can do is you can just try to see what will fit here, right? What will fit, what number should I write so that this is orthogonal to this is orthogonal to this, right? And it's when I take the inner product of this with itself, I must get 1. This with itself, I must get 1. This with this, I must get 0. This with this, I must get 0. That's one way of doing it. But the way we did it, that's a good exercise. I think you will get the answer that way. Let's see. If I write an x and a y here, so what condition do I get? If I do 2, so 3x, right? Plus 2y equal to 0. No, plus 2. I am taking the inner product of this character with this character. I can forget the 1 over 6 because it's a 0 on the other side, right? So here, and there is only one element, so it's 2 times 1. Here it is x times 1, but there are three elements, so it comes 3 times, 1 for each element. Here it is 2, right? Okay, let's with this is 2 minus 3x plus 2y. Okay, so what do you get? Clearly, if I subtract, I get 6x equal to 0, x equal to 0, y is equal to minus 1. You can just solve it like that. It must be like that. Okay? Now the question is, how do you find such a representation?
So what is done in the first row you have given first column, second column times third column. That inner product you are taking for the first equation.
I took the last row with the first row. Yeah. Last row with see this character. This character.
As a row and column, you can take anything. That is your choice. Right?
Yeah, but see, no, but see here I am not exactly doing the rows because I am doing times this. See,
You said that you have to multiply by the column.
no, but I am being a little careful. I am taking the inner product of this character with this character. See, if I just took blindly, I would get 2 plus x, no, but I have written 3x. So I am not literally, I am actually taking the inner product of this character with this character, but there is a 1 over 6 on the outside which I am forgetting because that side is a 0. If I do it with itself, for example, let's do it with itself. The inner product is 4 plus, yeah, so this square, but 3 times 0 square, right, 2 square, 1 times 2 square. Here it is 1, 2 times 1 square, but now I have to take a 1 over 6 for it to become 1, right? So 4 plus, yeah, so this is 1.
I was just asking that instead of rows, one can take column also.
You could take column, but then be careful because the correct thing is g by c. We put that root, square root of g by c. See, you can. Yeah, see, when you think of this as, if you want to just think of as this row being orthogonal to this row, you have to appropriately scale these columns, right? The square root of g by c or something we did, if you remember, right? C by g, square root of c by g we did, and then it is okay. If you are careful, yes, you can do it. Yeah.
That will be more difficult. More calculated.
Yeah, it might be necessary at a point sometimes. Okay? And that is, see, when you do research, that amount of work you cannot help. See, if it is doable in 5 days of hard work, you accept it as, or 5 years or 50 years of hard work, or maybe not 50, but it's okay. Okay, hard work is understood. You have to do it. Okay, it's only when you have no method, when you don't know how to do it, or even when you have a method, but that method will take, you can't run it even on big computers. That's when you really need an idea. Okay, is this okay? And how do we find such a representation? Well, that's again a good illustration. We did this. You can go back and look at the video of how we did this for how we actually found this representation. We calculate the character of, we said that Sn acts on 1 to n, and in here there is a subspace. So you linearize this, right? And so this acts on CE1, direct some CEN, and the subspace spanned by all lambda j ej such that with sigma lambda j equals 0, this is a invariant subspace, right? And what is its dimension? Well, total dimension is n, and this is one linear condition, so it's n minus 1. In this case, it's two-dimensional for S3. So it is that representation which gives you this. In general, this is an irreducible representation thanks to the problem that Surajit helped us do it, and therefore that is this representation. Okay. You can check that. Let's check. How do you check that? Say it is irreducible.
Any one dimension has to be checked. These are the only irreducibles.
So maybe you could take. Let's see. You could use the fact that chi is 1. I don't know if that is useful here. See, a representation V is irreducible if and only if the inner product chi V is 1. Yes. So you could try to use that. So if I write chi, so I know what the maybe it's not so easy. It's not so easy, but in any case, it's.
So if it is reducible, then you will have a subspace which is strictly lesser than. Then since a vector subspace is linear, so then we'll have some more linear condition with this one. So if you consider any other linear condition, summation alpha that where I varies from 1 to some.
Yeah. Okay. That's one. Yes, absolutely.
We use that it is G into N.
Absolutely.
The index is n and all the scalars are.
Absolutely. So what he is saying is, if you put if it's a subspace, it will be satisfying Aj lambda j equal to 0, some other linear condition, but no other linear condition will, or no other set of linear conditions will be invariant. Anyway, it's something, that problem you have done, right? There are many ways of doing this, not just a single way. So is this done now for S3? Are you happy, Sumit?
So this is irreducible, we have to prove. This representation.
Well, if you found one of this, irreducible representation must be of this character. If I show that, it is easy to show that this character is equal to that much, because you know that this is equal to trivial plus this one. So let's call this W. Why? Because you know that modulo W it is trivial. So then, and it is easy to compute the character of this, right? So chi of this, let's call this, so let's call this V. I want to call this V. Chi of V is equal to chi triv plus chi of W.
Trivial is that where all lambdas are same. The
Yep.
W is it and then trivial is it, right?
Yes.
Trivial
Trivial is the trivial representation.
lambda.
You can take that. You can take that to be the particular example of the trivial particular copy of the trivial representation. There is only one that copy. Yeah, and so it is easy to compute because this is easy to compute. What is chi v? Chi v on this is how many elements it fixes, right? It fixes so chi v on 1 is of course so let's write it here. Let's make a table. There is 1, there is 1, 2, and there is 1, 2, 1, 2, 3. So these are the values. This is 3, this is 1, this is 0. Because it is just the number of elements here fixed by this permutation. Because you are thinking of this as a basis for this and you are computing actually computing the trace of those matrices. The trace of this corresponding to this is the identity matrix. The matrix corresponding to this is the flip 1 and 2 and put 3, 0, 0, 1. The third column is 0, 0, 1. So the trace is 1. Here of course nothing is fixed. Therefore this is just the number of fixed numbers. So this is 0. Well, this is 1, 1, 1. So this must be the difference of those two. So it is 2, 0, minus 1. So you know that this must be this. See, so you know that this has this character. And if two representations have the same character, they are isomorphic. Characters determine representations. Right? It is like that fingerprint. Right? So you have shown that this must indeed be irreducible because you computed its character and it was equal to 2, 0, minus 1, which you know must be the character of some irreducible representation of dimension 2. Therefore, it is that irreducible representation. Okay?
But why you have computed this 310 that chi v?
I wanted to compute chi of W. I wanted to show that chi of W was 2, 0, minus 1.
So how does this prove that the chi of W has to be 3?
No, this does not, see, what? See, V is equal to triv plus W. Therefore, chi V is equal to chi triv plus chi W. Chi V is equal to this. Chi triv is equal to this. Therefore, chi W equals this. Okay? And once you have shown that chi W equal to this, then W must be equal to this irreducible representation because characters determine the representation. Yes, up to isomorphism. Huh? Yes, this is the number of fixed points minus 1, yes. Yeah, yeah. Standard representation, yes, indeed, that's going to be a general phenomena. That's going to be a general phenomena. So now you can actually compute. Yeah, we can actually, let's do it for S4. Okay, how about we do for S4? Is that okay? Is S3 okay now? Huh? Like I said, I don't mind if you ask questions, whatever kind of questions. We're here, I would want you to understand, right? And yes.
This kind of representation, only lesson is direct sum of W
not Sn, this representation.
With respect to that,
No, no, don't say that. That's the wrong, it's wrong use of language. I'm afraid that is not, so don't say that. Don't say it that way. This representation, which is the linearization of the defining action of Sn on letters 1 through n, that is a direct sum of two representations, trivial plus an irreducible representation W, which you call the standard representation. Okay, so the name for this is standard. This is standard, meaning the name standard is standard. Okay, okay. Now, what is your question?
now I have the next another circuit.
Yes.
Then we get a different expression of this. With S trivial plus.
You can define any representation you want. You could take 100 copies of this, 300 copies of this, 700 copies of this, do what you want. Okay? So, for example, let's do, for example,
So last question.
yes,
This chi of B you have computed on the left side.
Yes.
Chi of B you have computed that side. Now chi of W one can compute chi of B minus chi of 3.
yes.
So chi W you can't compute here, right? You have to compute first chi B and then chi 3.
That's the way I have done it.
That's the way you have done it.
That's the way I have done it. You might have another way of doing it.
So that may be a non-trivial task, right? Because chi tree is very easy to compute. Chi of B is also very easy to compute, and we know the.
It is well accepted that given, I did not say that there is a foolproof recipe for computing the character of any given representation. Okay, it may not be easy. We are doing mathematics. We are, it may not be. Nobody said it was easy. Okay, so
Because sometimes you have to calculate the character of W. It's not an easy task.
it's not an easy task, but often you have to look at it from some other angle or this angle. Yes, yeah. No, well, but even by hand if you do, it's not so difficult. What you could choose a basis consisting of E1 plus E2 minus 3E2 and E1 minus 3E1, E2 minus 3E2. E1 minus E3, E2 minus E3, right? And you write it out. You can actually compute the matrix and do it. It is not so difficult. Yeah, it just take a few minutes. It is less elegant than this. That's why I didn't do it that way. Okay, it is eminently doable. Okay. Okay, let's do S4 then. Okay, to answer Amit's question, let us here is a question. Take the standard representation and tensor it with the standard representation. Break it up into irreducibles.
Some of those lengths.
How would you do it?
So that is a linear.
See, you just follow your nose and do it. How do you break it up? You compute the character and take the each one with the you take the and how do you compute the character? What is the character of chi standard tensor chi standard? So in terms of this picture, what do I see? 4, 0, 1. So this is 4, 0, 1. This is 1. This is 1, 2. This is 1, 2, 3. Right? Now, I have to find how many copies of trivial, how many copies of standard, how many copies of sine. How do I do this? I take the inner product of this with this. If I do that, what do I get? 4 plus 1, plus 2 actually, plus 2 because there is a 2 here, 6 divided by 6. So it is 1. So it's trivial direction. Okay. What is the dimension of this? What is the dimension of this representation? This is 2 and this is 2. So the tensor product is 4 dimensional. Another way of saying it is that this number is 4. So it's 4 dimensional. Okay. True? Okay. Next, let's take the inner product of this 401 with this. Again I get 4, 0, 2, 6 divided by 1, which is 1 plus sine. Sine appears once.
That is again 1. Yeah.
That's again 1. So sine appears once. I take the inner product of this with this. So it is 4 into 1 into 1, 1 into 1 into 2, that is 4 plus 2, 6, divided by the cardinality of the group, which is 6, which is 1. It better be equal to an integer. If you didn't get, you made a mistake. Okay. Now 401 with this, 4 times 2, 8, 1 minus 1, 1 into minus 1, sorry, minus 1 times 2, 8 minus 2, 6, again 1. In the product.
Inner product,
Mm.
and again this
Yeah.
inner product with this is 1.
Mm.
So what actually we are showing, I didn't.
See, it is showing something remarkable. So, see, if I told you this representation times this representation, it's a complicated object, right? You have to compute those matrices. You reduced it. See, it's like fingerprinting. I just scan. It's like Aadhaar card. I get all your fingerprints, keep it with me, yeah, and then I say, oh, okay, who are you? I've never seen you. Come, look, show me your fingerprint, yeah, and then I check, and it checks, and so I say, okay, this is okay. Here is your data. Here is where you were born. You are from this, and here is how many times you took the, what you are doing. You are a student at time, etc., etc., etc. Yeah. Okay. So, right. So it's a remarkable, it's a beautiful theorem, right? How do you decompose? It is the chi v. You take the inner product of the character with the character of the irreducible representation, and that is the number of times that irreducible representation occurs in that. It's a set of beautiful facts.
Sir, if suppose this chi of left in that representation is not equal to 1 with your representation, because it is, as you said, this is going to form out an orthogonal, so that has to be 1. Inner product
And it has to be, inner product has to be an integer.
and inner product has to be an integer.
If you are taking to begin with a character, if you take any arbitrary class function, then need not be, because if I could divide this by, I could divide this by 5, and that is also a class function. But if it is a character, then the inner product with any irreducible character must be an integer.
And that integer is divided by the order of the group.
No. That integer is already divided by the order of the group. That the integer is in the product means divide by the order of the group.
And if it is equal to 1, then it has to be irreducible representation.
No,
That's
with
what it
itself.
is. With itself.
If the inner product of a character with itself is 1, then it is an irreducible character. If and only if, right? That follows. Okay, these are remarkable facts. These are not obvious. But I mean, remarkable on the one hand, but easy on the other. Once you know this beautiful theorem that the irreducible characters form an orthonormal basis for the
But sir,
class.
how you will this three direct sum with imaginary product? I mean, like from this chi of trivial is getting 1. So how it will trivial direct sum of sines? Again, in sine you got 1. So why you are writing this direct sum of sine? I mean,
No, this see, by Marshke's theorem, this must break up as a sum of irreducible representations. See, I am not. It may be a difficult thing to see what exactly that.
how many multiples of this?
How many multiples this is. Even when you can say it might be difficult. In this case, it might be easy, but it might. What sum of? How is it sitting inside there? That's a different question.
Got it, your point.
Okay.
You have done it in fact for CG. So general chi of CG.
Yeah.
Chi of A1 is how much multiplication?
Yeah. No, but see, V for that is true for any V. V is equal to V1 direct sum chi V chi 1 plus V2 direct sum, so many copies as chi V chi 2 dot dot dot. That is true for it.
Here has to be multiple of integer multiple.
Yes, it has to. If you didn't get, it means it's a mistake. Okay, but not for any class function, mind you, but it has to be a character. So if you take a representation, honest representation, any representation whatsoever, compute its character, take its inner product with any irreducible character, you must get an integer. It may be 0, but you must get a non-negative integer. No choice. If you didn't, then there is a mistake somewhere. You didn't do something right. Okay? Correct? Is this okay? So there are representations and representations and representations. Right? There are so many representations. Okay? So, but there are for a finite group there are only finitely many irreducible representations. I could take standard, tensor standard. For example, let's do standard, tensor standard. What do you do for that? Well, you can write it as standard, tensor standard, you can put bracket it, and then you know that this is equal to this. So it is triv plus sine plus standard, tensor standard. Okay, that becomes triv tensor standard plus sine tensor standard, direct sum standard tensor standard. Okay, and what is triv tensor standard? Well, I take the inner product of that gives me 2, 0, minus 1, which is the same. Triv tensor anything is equal to itself. This is standard. How about this? Sine tensor standard. So this is also standard. And this I know is triv plus standard plus sine plus standard. So the final answer is triv plus sine plus standard. There is 1, 2 and 3 here. Okay, so it's a calculus. You can make these computations. Okay, in the notes, if you see, in the notes that I gave you, there is it's called Clebsch-Gordon. This is goes by the names of Clebsch. It has a name. of mathematicians, I guess. So these are called Clebsch-Gordon coefficients. So general thing is you take some representation, you take its tensor product several times and see how it breaks up. Such a thing is called a Clebsch-Gordon theorem or Clebsch-Gordon coefficients. This, right? So it's a since you asked if it is easy to do, many of the, if we could do Clebsch-Gordon, let me say it quickly. If you could solve Clebsch-Gordon for any group, you would be, it would, I don't think it would be an exaggeration to say that you would be doing a lot of mathematics. If you can solve the Clebsch-Gordon problem, meaning if I take two irreducible representations, tensor them, see how it breaks up, and you know the answer. If you can find, if you have a recipe for knowing that answer in every case, that would involve lots of mathematics.
Can you two-page notes, we have written all those?
It is it's not 2-page notes, it's 3-page notes, it's on the 3rd page. Yes, there is a Clebsch-Gordon for S3, and it is done from an element, it says here from an elementary.
You are taking a tensor product of two irreducible representations.
That is one thing you could do there, and also there is something called, the word Plaithism is used. So for example, you could take 10th symmetric power of the standard representation, right? You can take sim n, right? Sim n is a, see, if I take a vector space, sim n of v makes sense. This you studied in your last semester, right? All symmetric tensors, right? Now, we saw that if a group acts on V, it acts naturally on any natural construction. So there is an action, sim, if V is a representation, sim of n of V is also a representation for G. So you could take sim n of the standard representation of S3 and ask how does it decompose into irreducible representations. Okay? This often involves, so you take that character, you take the sim n of that character, it may not be easy to compute, and then you have to see how it breaks up into irreducible representation. This often involves lots of beautiful mathematics. Okay? Should we do S4 or should we? Okay. No, let me finish the notes, so to speak. We wanted to talk about isotypical components, and there is also a second projection formula in the notes, in the second page of the notes. Let's do that and maybe come to S4 and the dihedral group on Thursday. All right? If you have time, I will do S4 as well, but maybe we won't have time. Okay, let's do. So isotypical components. So as always, base field is C for us. And G is a finite group. Right? what do we mean by isotypical components? So, given, so let V1 fix, let's take Vn be list of, be the list of events. Meaning no two, this is the list of, we know that this set is finite, you write them out each once. So there is exactly one, no two of them will be isomorphic. Okay? So the characters of these will form an orthonormal basis for the space of class functions of G with respect to our inner product. Okay. Now, given any representation V, let V equal to U1, U2, the two decompositions into irreducibles. Meaning as a direct sum of irreducibles, right? So you started with V, and then you started decomposing, I started decomposing. There is no reason why we should follow the same path, right? You found an irreducible representation, and then you took a complement, broke it up, and then went on. I took some other sub-representation, some other complement, and went on. There is a, we could choose entirely different paths to this. So maybe you ended up with this, I ended up with this. Okay? Now, let U upper j for 1 less than or equal to j less than or equal to n being the number of irreducible representations, U upper j be the sum of all those U sub k is between 1 and, so U sub k, so I am using upper and lower, be careful with different senses. So this is a lower k, such that UK is isomorphic to V1. Sorry, UK is isomorphic to VJ. UJ. Correct? So what I am doing, I am looking at all these which are isomorphic to V1. Their sum I am calling U upper one. Looking at all those that are isomorphic to V2, I call this U upper 2. Huh? And so we have U, oh sorry, V is equal to, you will agree that this is true, right? Because I just divided these up into n sets, those that are isomorphic to V1, those that are isomorphic to V2, I just arrange them and then take the sum. Okay? Similarly, so same, I mean, I'm not writing this out, but similarly, this W upper J will be W sub K such that W sub K is isomorphic to V sub J. Correct? So what you did was you took all these that are isomorphic to V1, isomorphic to V2, isomorphic to Vn, put them together. Now I took my decomposition, which could be a priori very different from yours, but then I also took all those that are isomorphic to V1, called it W1, I mean called their direct sum W1, W upper 1, W upper 1, took all these which are isomorphic to V2, called their sum W upper 2. Is this clear? Surajit looks, is this okay? Vi is the complete set of irreducible, the list of events. So some of these could be 0. Some of these could be 0. If for example, V is itself irreducible, one of these will be non-zero and the rest will be 0, for example.
Dimension of two representations, V1 and
They could very well be the same.
so then the two class, we are separating UI.
This is isomorphic as G, not as vector spaces. See, if the trivial representation is one dimensional, the sign representation is one dimensional, but they are not isomorphic as G spaces. This is isomorphism as G spaces. Right? Is that it could very well be that several of these have the same dimension. In fact, for an abelian group, we saw that they are all the same dimension. 1. They are non-isomorphic. Non-isomorphic as irreducible, as G.
So you are looking as a G space isomorphic copies of.
Yeah, always, it's always G as G modules or CG modules or G representations. I mean, we have so many different words for this.
Now you will say this as a vector space.
No, I'm going to say that then here is the claim. W1 equals, not isomorphic. This is equality. As subsets of V. This is a subset of V. This is a subset of V. This must be indeed the same subset, physically the same subset. It is not just isomorphism. Okay? Now I know even before you that you must get the number of copies of U1 that you get and the number of copies of V1 that you know is the same. That I know beforehand itself, right? Because that's chi V chi V1 in any case. Okay? So this is, and similarly, Wn is equal to Un is equal to U upper n is equal to Wn, and these are called. So if you do this, no matter what your decomposition is, you get the same answer. That is, U upper 1, W upper 1 are equal, no matter what your decomposition is, by the claim. Okay? These are called the irreducible components. These are called the isotypical components. This is called the isotypical component corresponding to V1. This is called the isotypical component corresponding to Vn. Okay, so the isotypical component of a representation as a subspace of that representation, as a subspace, as a subset of that representation is well defined. Okay? Okay, so we have to do, okay, so there are two things. First is I am making a claim I'm claiming this equality, I have to prove why they are equal. Right now I only claim this, I have not proved it for you. Right? Okay. So I have to prove that. Second, there is a nice question. Namely, okay, now that these are, now the isotypical components are unique, I know that this decomposition is unique. Right? Even this must be equal to this literally. So I have this. Now, I can talk about the projection to this. There is a unique projection to this. Namely, here it is identity, on these it's 0. Right? What is the formula for that projection? What is the formula for that projection?
The component of
Yes. So so there are two things we want to do. One is prove this claim by isotypical components. So two tasks. Prove uniqueness of isotypical components. Prove claim above. That is the uniqueness of isotypical components. This is a bad English because to define isotypical components you need the uniqueness. So, but I hope you understand what I'm saying. Okay? Then to projection formula, obtain a formula for the projection for the G projection to an isotypical component. Meaning to a given isotypical component. Right? Okay. These are the two things we want to do. Is this clear? Okay. Now notice the words that I've used. I've said the G projection. The, notice the here. It is not a projection. It is the G projection. Okay? So I'm claiming there is only, if I have a map from V to U1, it's a projection. First, it's a projection. Second, it must be a G morphism. Then it is unique.
That is, you have G components. This U1, U2, UNs are the G components. And for UN, this all U2 to UNs are the G components of U. So you have a one-on-one correspondence between the G projection and the G component.
Well, okay, I don't know, maybe you have the right idea, but it's not.
No, that is also for in like vector space. Hilbert space, you have a closed space, then you have a unique projection for Hilbert space. That's what I'm using.
Yeah. So the complement of this is unique.
Complement.
As a G complement, the only G complement is this. This is what you have.
Because you have taken all those jacks.
Well, because you have taken all those, that doesn't sound very, it sounds believable, but is it a proof?
Because U1 and U2 may not be isomorphic.
No, they are definitely not isomorphic.
Not isomorphic. Intersection is zero. So
Intersection is zero. In any case, see whether you are, it is a fact, we will just observe it in any case, that this is the unique G complement to U. There is no other G complement possible. Correct. There is projection means one-to-one correspondence with complements. G projection means one-to-one correspondence with G complements, and therefore this, in other words, we are saying this is the unique G complement. Okay, that's what we are saying. That is the projection, and we want a formula for that. There is a beautiful formula for that you can derive. Okay, it's very pretty. Okay, so we will do this. Okay, so these are the two things we want to do. Okay, let's go one by one. Okay, so let's this is 1, this is 2. So 1. That is, we are proving the claim, the uniqueness of the isotypical compound. So W1 is equal to U1, UN is equal to. Okay. So Uj as above is the natural, is the image of the natural map Vj tensor form G Vjd 2. Okay, so what I am claiming is Uj, look at this. I am taking Vj tensor, Hom as G modules from Vj to V. This is a vector space. This tensor, this vector space, there is a map to V. There is a natural map. And I am claiming Uj is the image of this. Right? Wj will be the image of this. So both Uj and Wj are the image of this. This will prove that, because here there is no dependence on the decomposition. Here there is a what we have shown is that this is dependent on the decomposition a priori, but this side is not. Therefore, this side is independent on the decomposition. That will prove it. Okay. Now let us think about this. What does this mean? See, this is, it looks very complicated, but exactly, it is sort of, you just follow your nose, right? It looks complicated. You're writing some symbols. Maybe you're not used to these symbols as they're being used, but if you treat them with a little, okay, doesn't matter what they mean. Just let's see what comes out and start using it. You will feel comfortable. And that's all there is to it. Okay. What is so to give a map from a tensor product, what do you have to do? But I have to give a map from this cross this, which is bilinear. What is a natural? Is there such a map? Yes. As Deepak was saying, there is an obvious map, right? So there is Vj cross Hom G Vj to V. To V, there is a natural pairing. So I will take V here, phi here. Where do I send it? Phi V. That's a natural way of getting an element of V out of this. This is bilinear. Yeah, this is obvious that it is bilinear. It's easy checking. And therefore, it goes down to by the universal property of the tensor product. So you have a map. Now, I want to claim that Uj claim image is Uj. Right? Okay. Now, let's see. there are two parts. One is image is contained in, whole of uj is contained in the image, and second,
Is continued.
right, okay. So what is uj? So two parts again. So let's say part 1, uj, u upper j is contained in the image. This is what I have to show. How do I show u upper j is contained in the image? Well, what is u upper j? U upper j is a direct sum of vj's, right? So, is the direct sum of u sub j such that uj is isomorphic, sorry, u lowercase such that u lowercase is isomorphic to v sub j. That was our definition, right? This is by definition. Correct? Okay. Now it is enough to show that each of these u sub k is in there. Enough to show each u sub k such that u sub k is isomorphic to v sub j is in the image. Right? But then if given such a j, given such a k, you choose an isomorphism. Vj, choose an isomorphism. So say psi from Vj to Uk. Right? This is a sub of V by definition. So this is a psi. So composing this psi with the inclusion gives you a morphism from Vj to V. You take, which is a G morphism, because this is a G morphism, this is a G isomorphism, and this inclusion is a G inclusion, because this is a G invariance. I mean, this is subspace, right? Therefore, if I choose here, if I put Vj tensor, the element psi composed with the inclusion here, then the image is precisely UK. See, I am saying something rather trivial. Okay, it's completely obvious what I am saying. It might look difficult because it is put in notation. Okay, I repeat, what I am saying is completely trivial. If you can see that it is, the point is to see that it is trivial. Okay, I am not doing any. No, it's just I am following my nose. Okay. Right. So the claim is that, see, so this is, let's call this inclusion I. So this is I is equal to inclusion. So if I look at Vj tensor, right? Now this is a subspace here. I am taking one element here and several elements here. Right? This is a subspace. Right? What is its image under the natural map? Well, I follow this with Vj and I get exactly UK. So this is image of this. So this call this phi or something. Okay, phi of this is equal to UK by construction. Okay, this finishes part 1 because we wanted to show uj was in the image. It was enough to show that each uk was in the image, and given such a uk, I have chosen. I have shown that that is in the image. Okay, so this is QED for part 1. Now for part 2, and I'll finish with that, is that the image is contained in uj, I have to, right? I want to prove uj equals the image, u upper j equals the image. We have shown that uj is contained in the image. Now we will show that image is contained in U upper J. Okay. Now for this, you claim enough to show. So you take U V to U upper K, K not equal to J. Projection along projection with respect to decomposition. You have a decomposition like this, right? So this is the projection, meaning I take an element of V, write it as a uniquely as a sum of one element of U1, one element of one element of U1, and take the element corresponding. This is what this means, right? Okay. Enough to show that image. So enough to show that enough to show the following. So let's call this pi upper K. Enough to show y upper K of image equal to 0 for all K not equal to J. That is, if I take an element, look at the image and look at the component, the other components are all 0. If I show, then that means it belongs entirely in U upper J, right? Correct? Okay. Now this follows because, okay, now here, so suppose you have Uj, okay. See, look at this, we have, again this is a triviality, if you just have to see it, Vj, Vg morphism to V to pi k. Pi k is this projection with respect to this decomposition. That's it. That goes to U upper K. So this is what we have to show.
But you have defined pi k like this, so that's obviously pi k is equal to 0, k not equal to 0. If k not equal to 0.
For on Uj it is 0. I have to show that on the image. See, the image, I want to show it's contained in Uj, so I want to show that on the pi k on the image is 0. See, what is not maybe obvious is that pi k on the Uj is 0, that is obvious. Pi k on the image is 0 is not maybe obvious. Okay, but again it is quite obvious because, see, this is the image, right? See, now you take an element in the image, right? What is it the image of? You take a phi, right? So this one, so take a non-zero element in the image. Okay, so let W be non-zero in the image. Right? How did that come about? It was some image of some element here, and an element here for some Vj, and then some tensor here, etc. Right? In other words, this W came about by. Okay. So the point I want to make is. Okay. See, what this U is V sub K some copies, right? right? Okay, let's write it. Let's think abstractly. So this is a G map. You agree? This is a G map where this is a G module. This is a trivial G module. If you think of this as a trivial G module, then this is a G map. Okay? Okay, I can say a little more at that point, but for lack of time I'm not. So this is equal to Vj up some copies. Because this is Vj tensor trivial module. Okay? So now look at this. This is isomorphic as a G module to Vj some copies of Vj. This is isomorphic to Vk some copies. Right? But how can that be? The only, and these are all G maps. This is a G map. This is a G map. This is a G map. How can there be a map? Why this is, okay. So if you have a trivial G module, how does this break up as a G module? It breaks up into what? You take any line. You just break it up into as a one-dimensional vectors as a lines and write it as a direct sum of trivial plus trivial plus trivial as many times as the dimension of this. Okay, so then this becomes Vj tensor first line, which is trivial module. So yes, Vj tensor trivial plus Vj tensor trivial plus Vj tensor trivial plus Vj tensor trivial, right? Actually, this is Vj as many times as the dimension of this. Yeah, correct. That's it. So this is Vj some copies, this is Vk some copies, but if j is not equal to k, this is a G map, there can't be any G map. That's the proof. Okay? Since if j is not equal to k, the composition must be 0. So it's completely, it's rather trivial what I'm, at the end, the point is, how do you realize the isotypical component? It is Vj, it is this, it is the image of this. Okay, and what is involved in that proof is just some very basic things about, it is not a very deep fact at all. It is not like this statement about, for if you wish, Frobenius's theorem, that the characters form a orthonormal basis for class functions, right? For the space of class functions. That's a theorem, right? It required Frobenius to see. But this one is more, once you make the definitions, it's sort of obvious. There's nothing much going on here. Okay? So we've done part 1. We've shown that the isotypical components are unique. Now we will do one more bit. We will derive a formula for the projection, the G projection, to this isotypical component. Okay, that is the next part. So since this is being video recorded, I hope you will watch the video if something is not clear. And by all means, I repeat, ask questions. Okay, I will be happy to answer any number of, I will be happy to repeat this, I will be happy to clarify this, do whatever it takes for you to understand. Okay? With that, and then we do some examples maybe of S4, maybe of diagram groups, character tables, and that will bring us to the that will bring us to the midterm examination next week on Wednesday at 10 o'clock, did we say?
Yes, sir.
10 o'clock, I will book a room, hopefully, I'll find a slightly bigger room.
So
Huh?
yes,
Up to tomorrow?
Thursday.
Up to Thursday. Character table, right? We've already started talking about it. I'm not doing anything more. So whatever we do until Thursday. Yeah?
Sir,
Yeah.
I have one confusion.
Yes.